Good afternoon, everyone. So welcome to this last lecture of the course ODE. So we're going to step up with our study. So let's just a few words about what we did in this chapter. So this was chapter 3 about two-dimensional linear systems. So yeah, so we studied non-zero and different eigenvalues. Real, so real is missing here. So non-zero, real, distinct eigenvalues, right? This correspond to nodes or saddle nodes. Then we studied in detail complex eigenvalues. These correspond to either focus or centers. And then other cases. So we studied the case where one eigenvalue was with a real part 0. The case where the matrix was diagonal, and then now we are dealing with the case where we cannot diagonalize A, and the eigenvalue is multiple. So we're considering all right, so there's some noise here. All right, so I suggest you to try to solve this exercise, and so try to do it. Try to so find solutions and try to draw, to sketch the trajectories of the solutions, and so we can discuss after 10 minutes. So see you in 10 minutes. Oh, oh, sorry. So, yeah, sorry, my microphone was off. Okay, let's do it again. Let's do it again. So we are dealing with this equation. So my A is given by 1, 1, minus 4, minus 3. The trace is minus 2. The determinant is 1. So if I look at the expression trace of A squared minus 4, determinant of A is 0. And so by applying the usual formula, I obtain one double eigenvalue, which is equal to minus 1. This means that my A, I can't diagonalize it, all right? So, but we are going to look for eigenvector, for an eigenvector associated with this eigenvalue. And so I just here I compute A minus lambda identity, which gives this matrix. And if I solve this equation 2x plus y equals 0, I obtain y equals minus 2x. And if I choose x to be 1, I obtain y to be minus 2. All right. And so as usual, then alpha exponential lambda t v1 is a solution of the ODE, whatever alpha is. All right. Okay, if A had two distinct eigenvalues, I will do the same for the second eigenvalue, and I will obtain all the solutions. But here, that's not the case. So instead, we're looking for a V2 such that A minus lambda identity V2 equals V1. So if I write what A is, I obtain this equation, and then for the first line, I obtain 2x plus y equals 1. And so if I choose x to be 0, I obtain y equals 1, and then I obtain my V2. All right? Okay, now, what did I get? So now, let us summarize what we obtain. So we first have that A V1 equals lambda V1. And also we have A. So let's do it in details. A minus lambda identity V2 equals V1, which implies that A V2 equals lambda V2 plus V1. All right. So let's write it as the matrix. So AV1. So here my V1, V2 means the matrix for which the components are the vectors V1 and V2. So, and here I write V1, V2 like this. So AV1 equals lambda V1. So I just do the computation product of two matrices. And if I want to obtain, so AV1 is lambda V1. So if I want to obtain as the first vector of the product, if I want to obtain lambda v1, I just write that. Okay, because when I do the product here, line versus column, I get lambda v1 in the first column, right? And the same now for the second column. So if I want to obtain in the second column lambda v2 plus v1, so I put a 1 here and a lambda here, right? Because when I do this line times this column, it's v1 plus lambda v2, and this is equal to av2. All right. Okay, so as usual now, if I call this matrix P, and this one I will call H, I get that AP equals PH, or A equals PH, P minus 1. So instead of solving x prime equals A x, this is the same that x prime equals PH, P minus 1 x, and this is the same as y prime equals H y with y equals P minus 1 x, which is the same as x equals Py. All right. So now let's solve this equation. So x prime equals lambda x plus y, y prime equals lambda y, which is my equation, y prime equals h y. So the second equation is easy to solve. So I have that y of t equals exponential lambda t y0. And then I can solve x prime equals lambda x plus y. This is classical, so I will do again for you. I could write the solution directly and prove it. So again, if I multiply this equation by exponential minus lambda t here, I recognize here the derivative of exponential minus lambda t x. So if I take the integral between 0 and t, I get that exponential minus lambda t x minus x0 equals integral between 0 and t of exponential lambda s y of s ds. This is quite general, so this gives x of t equals exponential lambda t x0 plus the integral between 0 and t of exponential lambda t minus s y of s ds. All right, now if I replace y of s by its value. So I just want to write it here. Let's do that here. So I get x of t equals exponential lambda t x0 plus exponential lambda t y0. Any question? I went a little bit fast. So let's do that. Any question? So I got the solution for the system capital Y prime equals H capital Y, right? So let's try to go a little bit further. So what do I have? Let's write it again. So I obtain y of t equals y node exponential lambda t, and x of t equals exponential lambda t x node plus t exponential lambda t y node. All right, so we can do several things here. I'm just going to write because afterwards I will need that. So this means that y of t, I can write it I can write it as, for example, so exponential lambda t x node. So one zero plus exponential lambda t y node, and this is t and 1. So one of the goals here is so I want to represent this solution here. So I'm going to do other things. To do that, so one of the things I'm going to look at what's the solution looks like in the neighborhood of 0. So to do that, it's not the first time I can look at the y of t divided by x of t. So this is what? This is y node exponential lambda t divided by x node exponential lambda t plus t exponential lambda t y node. And I can simplify by exponential lambda t, so I get y node divided by x node plus t y node, and this is going to 0 when t is going to plus infinity. All right, so this means that the trajectories are tangent to the x-axis on the neighborhood of 0, 0. So now I guess we can try to sketch the trajectories. All right, so I remind my age was, so it was x prime equals lambda x plus y, and y prime equals y, lambda y, sorry. Okay, which means that, so here lambda is -1. So if I look at the null lines, I have that the x prime greater than 0 is equivalent to minus x plus y greater than 0, which means y greater than x. So we have first null line here. Okay, let's do it like that. Oh, so this is a null line. And okay, and the other null line is just if I look at y prime greater than 0 is the same that minus y greater than 0, which is y negative. All right, so here I have here y prime is greater than 0. Here y prime is less than 0. Here x prime is greater than 0. Here x prime is less than 0. Okay. All right, so after that, so if you look at the solutions, if I take y node to be 0, so the solutions are right like that. So here, if y node equals to 0, I have solutions lying on the axis this one. Okay, so let's do it. Oh. So this is a solution. And then let's draw another one. So, for example, here. So when the solution cross here, my x changes its direction. So I have that. So one of the solution is like that, and then is tangent here. So here is the solution. And on the other side, it's the same here. Let's do, for example, that. And it's like that. All right. And that's it. I have all the solutions that will do that, right? Can do another one. Oops. Oh, sorry. So I do it like that here. So of course, it cannot pass this. Kind of, right? All right, so this is the solution of y prime equals hy. Any questions? All right, so now, okay, that's good. But in fact, then, so I can obtain now the solutions of the original system. So there's a question. Y equals x. This is an incline, meaning that the trajectory changes direction with respect to the x variable. So now my goal is to draw, because I can do that here, the solutions of my original system. So x prime equals ax. And for that, I'm going to, for example, so I know, so this is the solution for the system y, capital Y prime equals ay. And if you remember, I wrote it like that. So I wrote it y of t equals, so if you don't mind, I will just put some tildes here, because now I want also the solution of my original system. So I can write it as, so if I put the x till 0 here, lambda t, then 0, and plus exponential lambda t y node t1. Okay, but now I know that my solution x of t equals py. And so I will apply that. So if I apply p here, p times 1, 0 is just the first vector of p, and the first vector of p is v1. So when I will do the product py here, I will obtain x till node exponential lambda t v1. I knew that this one already was a solution, plus, so p, so I will do it, I will spread this one, so plus exponential lambda y tilde node, yeah, I will do. So t v1 plus, so, and then a times 0, 1 is v2, so plus exponential lambda t y node v2. Okay, so let's do it again. So I have that x. Oh. Okay. No. Okay, so okay, so I recall that we have x of t equals x node exponential 1 plus y node t exponential 1, and y of t equals y node exponential 1. So I can write that as, so I will put some tildes here because I want to write yt. I want to differentiate between the solution of x prime equals ax and y prime equals hy. So I can write it as x tilde node times exponential lambda t 1, 0 plus y node exponential lambda t 1. All right. Okay, now if I do p y of t, which is x of t, this so is x tilde node exponential lambda t, and p times 1, 0, it's v1 plus, so this term I will separate it. So first plus x tilde node exponential lambda t. So, and here it's 1, 0, and p times 1, 0, again, it's v1. All right. And the remaining term is x tilde node exponential lambda t, p times 0, 1, which is v. All right. And so when you are going, for example, to do the division yt divided by x of t, where x of t equals x of t, y of t, right? So if you do that, and if you look at what's the limit of that, I have to look at the leading coefficients, the coefficients of higher degree, if you want. So this is the one, right? You can prove that, it's not hard. And so here I will get that this is converging to v21 divided by v11, where with v1 equals v11, v21. All right. So now we can draw the solutions So yeah, it's good to have to draw the null lines. So if I remind the initial system, it was x. Oops. No. So it was x prime equals x plus y minus 4x minus 3y. So the first null line is x prime greater than 0 is the same as x plus y greater than 0, which is y greater than minus x. And y prime equals 0 is equivalent to y less than minus 4 thirds x. So I will draw my null lines. So here, so when here I have x prime greater than 0, and here x prime negative. For the second null line, I obtain here y prime greater than 0, and here y prime negative. Okay, what I want also is my first eigenvector, which was v1, which was 1 minus 2. So 1 minus 2, let's do it like that. Right, so I know that those are solutions, and the other ones let's draw one here. So let's draw one here in blue, for example. So it's going to do like that. Okay, I know that the trajectories are tangent to v1. And on the other side, let's do it in green. It's the same. Here I have a tangent here, a tangent here. And it's going like that. All right. All right, so just a remark. So I computed the solutions. I draw it. I will show you the solutions made with the drawings made with the computer. But just before, I want to make a remark because so this for the solution of, so if I look at x prime equals lambda x plus y and y prime equals lambda y. So the solutions that we found were y of t equals y node exponential lambda t, and x of t equals x node exponential lambda t plus y node t exponential lambda t. But those one I can compute it. I can compute x as a function of t, because, for example, so let's assume I choose x node and y node positive. In this case, we saw that x of t and y of t will remain positive. So in this case, so I can compute t here, right? Because I will get log of y equals log of y node plus lambda t. This gives t equals log of y minus log of y node divided by lambda. And then, so I obtain that x equals, this is y, but this is x node divided by y node times y plus y times t, but t is 1 divided by lambda log of y minus log of y node. All right, so I can write x as a function of y explicitly in this case. All right, so that's it. Let's go back to our PowerPoint. Let's go back to our point. All right. Okay, so here are the solutions. So here, actually, I computed the solution with the exact solution. Those are the real solutions of the system. And here, so at the left, so at the left are the solutions with the system. So let's write it. So here, it's y prime equals h y, while here it's x prime equals a x. And as you know, you have that x equals py. All right. So all right, so let's start. So now we are discussing briefly the nonlinear systems. So let's go, and we already did it actually, but okay, let's go through it again. So now we're coming back to the more general. So f is not linear anymore. So here m equals 2, right? And so stationary points are important. And when f is nonlinear, more things can happen, right? So yeah, we have to first look at the stationary points of our ordinary differential equation. So when none of the eigenvalues of the Jacobian of f at the stationary point has a real part, which is 0, then it is called an hyperbolic point, right? And if all the eigenvalues of the Jacobian have a negative real part, it's called a sink, right? My stationary point is a sink when all the eigenvalues have a negative real part. And it's a source if all the eigenvalues have a positive real part. When it has negative and positive real parts eigenvalues, then it is a saddle node. So now, if all the eigenvalues are real, it's called the node. And if the eigenvalues are complex with non-zero real part, it's called a focus. So now you have the definition of the stability. I already gave that to you, but you can work on that. And basically, a stationary point is stable if what? If so, for any ball which is represented here by the number epsilon, I can choose a neighborhood of my stationary point such that my trajectory won't leave the ball of radius epsilon if I start in the ball of radius delta, right? This is the stability, meaning that I can ensure that my trajectory will stay in a ball as small as I want, all right? And a stable point, which furthermore satisfies that the trajectory converges to u star, to the stationary point, when t is going to plus infinity, is asymptotically stable. Well, the stationary point which is not stable is called unstable, right? So now we can do the combination, because if a node is stable, you have a stable node, etc., etc. Okay, now we have a theorem. And it says that a sink is asymptotically stable, while a source or a saddle node are unstable. So what we are going to do now is we are going to prove this theorem in a special case, right? So let's do that. So we are going to prove the theorem in the case where the two eigenvalues are distinct, real, and negative, right? So we are going to prove the theorem in the case so lambda 1 is different from lambda 2. So lambda 1 and lambda 2 are the eigenvalues of the Jacobian. And so, for example, the 1 is less than lambda 2, it's less than 0. And so they are real. Okay, in this case, so if I look after changes of variables, the change of variables, we did it a couple of times, it's the same. So after change of variables, the system writes in this case we can write it as x prime equals lambda 1 x plus some function which contains only the terms with quadratic order or above, and y prime equals lambda y plus a function g x of y. So with the assumption that the norm of f t divided by the norm x y goes to 0 when the norm of x y goes to 0. This is because f and g do not contain linear terms, all right? So I put all the terms which are quadratic or above, right? So the idea, you just do the linear transformation that we did for linear systems, right, with the P. So to obtain that, just a comment. Yeah, that's that is just is the chain of variable y equals P minus 1x. So you do that, and then yes, you have the other nonlinear terms, right? So you can write that. And then once you have that, you can look at, we call H, let's call H P equals, for example, x squared plus y squared, right? So now if I look at the derivative of H, this is 2x prime plus 2y prime, which is equal to 2 lambda 1 x squared plus 2 lambda 2 y squared plus x f xy plus y g right? And all right, now this is less than. This is less than. So we made the assumption that lambda 1 is less than lambda 2. So this is less than 2 lambda 2 because it's negative, right? X squared plus y squared, but this is H, plus, and now I apply the Cauchy-Schwarz inequality. So plus the norm of xy times the norm of fp. This is a Cauchy-Schwarz inequality. Okay, and then I can put this is less than 2 lambda h plus h and fg divided by xy. But I know that this is converging to 0, so I can put. So finally, what I get that h prime is less than h times 2 lambda 2 plus the norm of fg divided by norm of y. So now, if I am close enough from 0, 0, so without loss of generality, I assume that my fixed point is 0, 0. I can always come to that by a change of variables. Right? But now, since lambda 2 is negative, this will remain less than some constant. So for example, this is less than lambda 2h, as soon as xy is close enough of 0, 0. So then when this inequality will is true when xy is close enough to 0, but when this is true, I can again I do this computation. So I have that exponential minus lambda t h prime is negative, and so I got h of t is less than exponential lambda t h of 0. So now my h of t is decreasing, so my x and y will always stay in this small ball, right? And I get the stability and the asymptotic stability. That's it.